Okay, so this is a video about graphs of logarithmic functions. What we're going to look at today, by the end of this presentation, you will be able to draw a log to the AX graph, translate that graph horizontally and vertically, dilate the graph from the X and Y axes, reflect the graph in the X and Y axes, and use mapping to identify transformations in a combination situation. So let's get started. Here's a graph of y equals 2 to the power of x. So I'll look here, x equals minus 3. Here's my little, and here x equals minus 3. So that's 1 over x to the minus, that's x to the minus 3, which is 1 over x cubed, which is 1 over 8. The next one, 1 over x squared, which is 1 over 4. When x is minus 1, that's 1 over 1. 1 over 2. When x is 0, 2 to the power of 0 is 1. Then we go 2, 4, and 8. Let's try and draw that on our little graph here. When x is minus 3, 1, 8. When x is minus 2, 1 quarter. Which is 1 half. 1, 2, 4, and 8. And so the graph that we get is this classic sort of hockey stick shaped graph, and I'm not drawing that particularly accurately. You get this hockey, it gets closer and closer to the x-axis here, and as I go further in the positive, it gets higher up. The important point goes through x equals 1. So let's try and draw that a little bit better, perhaps. Don't know if making it thicker is actually helping. Now let's look at the same points. This time I'm looking at a logarithm graph. And what we know about logarithms, we know that if y equals a to the x, a to the power of x, then x equals log to the base a of y. It's a g, that one. And you notice that the x and the y have swapped and the base has stayed the same. So if I look at this, what's that telling me? This is telling me basically that x and y have swapped. So if I start here, down here, now x is 1/8, y is minus 3. X is 1 quarter, y is minus 2. X is 1 half, y is minus 1. When x is 1, y is 0. When x is 2, y is 1. When x is 4, y is 2. And when x is 8, y is 3. Let's try and draw that on our graph. When x is 1/8, y is minus 3. That's down here somewhere. When x is a half, a quarter, y is minus 2. When x is a half, y is minus 1. When x is 0, y equals 1. When x is 1, y equals 0. When x is 2, y equals 1. When x is 4, y equals 2. And when x is 8, y equals 3, which is sort of out there somewhere. What are we going to end up with here? We've got this classic sort of curve. And you'll notice it gets closer and closer and closer to 0, but never actually touches as an asymptotic behavior at 0. x equals 0. And that should be some sort of smooth curve. I'm obviously still learning with the drawing of the lines here. We're trying to get some sort of smooth curved. What you look at that and you say, well, that looks really much like a reflection. If I can somehow along here, I'm going to dot a line y equals x, and you could see that's a pretty good reflection. This one up here, y equals 2 to the x. This one, y equals log to the base 2 of x. Notice the bases have stayed the same, the x and y have changed. Okay, so that's what the basic shape of the graph looks like. What do we know about this graph? The log graph always has that same characteristic shape. That's the parent function. It's based around these couple of points when x equals 1, y equals 0. Okay, let's start transforming these by looking at some of the variations. I'm now going to use the calculator to draw my graphs rather than my attempts by hand. What do we know? We're going to draw y equals log to the base e. So in blue, I've got y equal log to the base e of x. And now I'm going to draw y as a log to the base e, or the natural logarithm, x plus 2. What does the plus 2 do? Well, that's the one drawn in red, and you can see that every value has now moved up 2 spaces. Plus 2. Every point on the graph has moved up 2 spaces. And so x equals 1, y equals 0 is now x equals 1, y equals 2. So what's happened here, if this is our original xy point, on the second graph the x has stayed the same, it's y plus 2. So that's our transformation. Every point on the graph has moved up 2 places. Now we're going to look at the next transformation. What if I do this graph? Y equals log e to the x plus 2. Notice the x plus 2 is in the brackets, inside the brackets this time, not outside. So we've still got our standard y equals log e to the x graph. And when I draw this new graph, what do you notice? Every point here has moved parallel to the y-axis, parallel to the x-axis, I should say, 2 point places. So it's moved, every point on this graph has moved parallel to the y-axis, to the x-axis, parallel to the x-axis, 2 places. Now, what does that mean for our xy point? Well, any point xy on the original graph becomes x minus 2. The y coordinate stays the same. So the new point here is x, the original x minus 2, and the same y. Notice, because when we look at the equation, the plus 2 is inside the bracket, so we do the opposite. So it's a minus 2. It's a shift of minus 2 places. Okay, next one we want to look at is, what if I put a 2 out the front? So this is 2 times log e to the x. What's going to happen here? Well, I've made the graph a little bit bigger here so that we can see exactly what's happening. We're changing the y value. So with 2 log e to the x, we're doing something to the y, the shape, the y value. So it's actually moving from the x-axis. So at every point on this graph, if you look at our graph here, I'll find my pen again, if I can find my pen. This distance here, I've doubled. Add that same distance again. So for every x value, the y value is now twice as far from the x-axis. Twice as far from the x-axis. And the same thing has happened down here. So you look at this point here, it's that distance away, now it's that distance away. It's twice as far from the x-axis. So that's what we call a dilation by a factor of 2 from the x-axis. So we say from the x-axis. Dilation by a factor of 2 from the x-axis. Now let's see, what if we put the 2 inside the bracket? So this is now, instead of taking the log of the log of x, we're taking the log of 2x. What's going to happen here? Again, I've made the graph bigger so that we can see what's happening. This is a bit harder to see. Here's my original point here, and here's where that same point is being dilated to. What you'll notice, it's now half of the original distance from the y-axis. So it's half of the original distance from the y-axis. So this point here is now moved to there. It's been moved, well, to there. So it's half of the original distance that it was from the y-axis. So because it's inside the bracket, its dilation, so we call this dilation by a factor of 1/2 from the y-axis. And you can look down here as well, and you can see that this point is now moved to there. It's 1/2 of where it was before. So if you look at this, our original xy point here is now a half x, but the y coordinate stays the same. So a half x, but the y coordinate stays the same. Okay, now we're talking about reflection. I'm putting a negative sign out the front. What's this going to look like? Well, you can see in red that it's a straight reflection. So this is our original point here, x and y. Then this has become, the x has stayed the same, and it's a minus y. So we would say this is reflected in the x-axis. Reflected in the x-axis. Now, how would we compare that? Let's compare that to reflection in the y-axis. Well, you look at this graph. Notice that this time the negative sign is inside the bracket, so that's going to reflect in the y-axis. So this point here, x and y, is going to become this point over here, which is negative x and y. And you can see the y-axis here is the line of symmetry. Okay, so there are all of the different transformations we start with our parent function. So always think about, this is our parent function. What has happened to the parent function? Well, if we plus c, c can be any value, we translate c units from the x-axis. If we subtract b, we translate b units from the y-axis. If we multiply by a number outside, we're actually changing the y value, which means a dilation from the x-axis. If we're putting the number in here, we're changing the x value, which is a dilation from the y-axis. So I think I said that right. Let's try that again. So dilation here, we're changing the y value, dilated from the x-axis. Changing the x value, dilates from the y-axis. And then we've got our reflection. This time we're affecting the x value, so it's reflecting in the y-axis. This one's affecting the y value, so we're reflecting in the x-axis. I would have this summary written down in my summary book somewhere, and this would be a good thing to come back to later in the year. Okay, let's try and describe the transformations. So we're trying to do this, which turn y equals log e to the x into y equals 3 log e to the 2x minus 1, all in brackets, plus 3. Well, the first thing we do is write out our equation. I'll find my pen again. So we got y equals 3 log e 2x take 1 plus 3. And we're trying to make this look as much as possible like the parent function. So I'm going to subtract 3 from both sides. I'm going to divide by 3 equals log e to the 2x take 1. Now I'm trying to make it look like the parent function. This is what we call the transformed function. So I'm going to make it x dash and y dash to say transformed x, transformed y. What do you notice? I put a little dash here just to distinguish. The original equation is y equals log e to the x. So if you relate this and this, that tells me that y equals the old y. In its place, I've put the transformed y, take 3 over 3. Now I want to know, what have we done to the old y? Well, I'm going to times it by 3, and I'm going equals the new y, take 3, and so 3y plus 3 equals the transformed or the new y. And I do the same thing here with the x and the x. In place of the old x, I now have 2 times the transformed x take 1. So x plus 1 equals 2 times the transformed x. So x plus 1, I'm going to divide by 2. Divide by 2 equals the new x. What does that mean? That means that for every xy point on the old graph, the x has become a half x plus a half, and the y has become 3y plus 3. Let's write that down in terms of what we had to describe the translations and the transformations. Well, the dilation, we've got a dilation by factor of 1/2 from the y-axis. There's our dilation by factor of 1/2 from the y-axis. we've got a dilation by a factor of 3 from the x-axis. We normally write the dilations first. So there's our dilation. There's no reflection going on here, but there is a translation. Translation of half a unit. This is going in the plus direction, which is to the right. Positive half a unit from the y-axis. And, excuse my handwriting, translation of positive 3 units from the x-axis. So that's pretty much what's happening here. Where would we plot this graph? Well, you'd say on the original graph you might have the point 0, 1. Where's that going to be now? Well, x equals 0, so 0 divided by 2 is still 0 plus a half. So that's going to be at a half. And 1, y equals 1, so 3y. So 3 ones are 3 plus 3 is 6. So our original graph will go through the point 0, 1. Our new graph goes through the point 1/2, 6. When x equals e on this one, y equals 1 on the original graph, well, that would just become a half e plus a half for my x coordinate, and my y coordinate I've written that back to front, haven't I? Sorry. Just scrub this out for a minute. When x equals 1, y equals 0 is what I should be saying. When x equals 1, y equals 0. So 1/2 plus a half, it should be 1. And if 3y plus 3, that should be 0. It becomes 1, 3. Okay, little mistake there. Hopefully I've picked that up. So just go back and check that, because I did make a mistake with my original point. Okay, can we do that by a shortcut? Well, there is a little shortcut that if you become more familiar with this, you can look straight at the graph and you can say 3 log e. Now, I'm going to take my 2 out as a common factor and make that x take a half. Why do I do that? Because I want the x to have a coefficient of 1 plus 3. Now you say anything that happens inside the brackets is happening from the y-axis. So we've got dilation by a factor of a half. We've got moving 1/2 unit from the y-axis. Everything that's happening outside the bracket is from the x-axis. So that's telling me dilation by a factor of 3 from the x-axis, and we're moving 3 units from the x-axis. So let's see if that makes sense. So remember here, everything which is outside the brackets is happening from the x-axis. Everything which is inside the bracket, we do the opposite of. So if that's a minus inside the bracket, we do a plus. If that's a times by 2, we're timesing by a half, or we're dividing by 2. So anything inside the bracket, and so that's this part is that's happening to the x, so it's from the y-axis. and this part which is happening to the y value is from the x-axis. So if it's outside the bracket, you just do whatever it says. If it's inside the bracket, you do the opposite. Okay. So in this presentation we've talked about drawing a log to the AX. A can be any base. I've used base E for most of my graphs, but you can use any base. Translate that graph horizontally and vertically, dilate the graph, reflect the graph, and use mapping to identify transformations in a combination situation. And that's the end for this video.